Unit 3, Worksheet 4, Interpreting Graphs of Accelerated Motion, Object C. Now, Object C, we have a velocity versus time graph. On this graph specifically, we have a constant slope, starting at a velocity of -3 meters per second, ending at a velocity of -9 meters per second, and that occurred over 8 seconds. The slope of a velocity versus time graph is going to be the acceleration of the object. We can calculate that looking at the change in velocity over the change in time, which is going to be how we would calculate the slope on this type of graph. So in order to calculate the average acceleration of this object, which I'm going to actually do first here, we're going to look at the change in velocity over the change in time. Here we end up at a velocity of -9 meters per second. That was at a time of 8 seconds. And we start off at a velocity of -3 meters per second, and that was at a time of 0 seconds. So our change in velocity here, -9 minus -3, is -6 meters per second, and that occurred over 8 seconds. So our acceleration will be -0.75 meters per second each second. That's the acceleration of this object. We got that by looking at the slope. Now, the reason why I wanted to do that first is because we have two different ways that we can figure out displacement from a velocity versus time graph. We have a mathematic way and a graph way. I'm going to start off with the mathematic way for part C, and then I'm going to do the graph way for part D. So for part C, I'm going to end up with our mathematical approach. We have an equation where we can use displacement by using a kinematic equation. One of the kinematic equations that we have that includes displacement is going to be this one. Honestly, we can end up figuring out a lot because we do know displacement is equal to final position minus initial position. So we could use a different kinematic equation and rearrange it. But I'm just going to start off with this one because it's already set up with displacement. I can rearrange this equation so that way v squared minus v0 squared is equal to 2 times acceleration times our change in position, or the displacement. So that way our change in position is equal to v squared minus v0 squared all over 2a. So once I have my equation set up like that, I can end up using it to try to figure out the displacement from 0 to 4 seconds by looking at the velocities there. The velocity at 4 seconds is -6 meters per second, and we square that. We subtract that from the starting velocity, the velocity at 0 seconds, which is -3 meters per second. All of that gets squared, times 2 times the acceleration of the object, which is -0.75 meters per second squared. So when I simplify this down, that'll be 36 meters squared over second squared, minus 9 meters squared over second squared, all over -1.5 meters per second squared. 36 minus 9 is 27 meters squared over second squared. All of that is going to be over -1.5 meters per square second. 27 over -1.5 is going to be -18. The second squared cancels out, as does one of the meters. So our displacement here would be -18 meters. So that would be the math way, where we end up using one of our kinematic equations to figure out displacement. A non-math way is to look at a graph way. We can figure out the displacement by looking at the area under the curve on a velocity time graph. What I mean by that is by looking at where the curve is and figuring out the area between that curve and the time axis. So if we do that for part D, from 4 to 8 seconds, from here to here, essentially what we're going to be doing is trying to figure out the area of this shape, which is not super intuitive the way it is, so we can break it up into two easier shapes, a rectangle and a triangle. So if we have the displacement of region A, that's a rectangle, the width of which would be 4 to 8 seconds, so that's 4 seconds. times the height, which would be 0 to -6 meters per second. 4 times -6 is -24, and our seconds on top would cancel out with seconds on bottom. So that way, in that A region, the rectangular region, the object would be displaced by 24 meters in the negative direction. If we look at the displacement in region B, that's a triangle. The area of a triangle is 1/2 base times height. The base here would be the same as the base of the rectangle, which is 4 to 8 seconds, which is 4 seconds, times the height. We go from -6 to -9, so that is a height of -3 meters per second. 1/2 times 4 times -3 is going to be -6, and our seconds still cancel out. So that way the displacement of region B is -6 meters. So the total displacement from 4 to 8 seconds is just combining those two displacements, which would be -30 meters. Two different ways to end up with the same type of solution. For the displacement from 0 to 4 seconds, we could have done it by looking at the area, or we could have done it by looking at the equation, which is what I elected to do. For the displacement from 4 to 8 seconds, we once again could have done it either the mathematical way or the graphical way, but I elected to go with the graphical way there. If you do decide to go with the math solution, you do, however, need to solve for the acceleration first. And it will be way more simple if there's a single uniform acceleration in the entire duration of the time that you are looking at. Otherwise, you'll need to apply another kinematic equation to figure out the displacement.